Hi, I'm Dane Underwood,
Felipe Cardenas.
Isaac Geisler.
I'm Kumar Kara.
and we're here to present to you today our design of a transoceanic cable protection system. Currently, submarine fiber optic cables carry 99% of all international communications, and billions of dollars are invested in this network. It's also been growing by about 30%, 36% annually since 2007. And between 100 and 150 cable faults occur per year, causing damage to this system. Up to 20% of the causes of this damage are never identified, and each damage incident costs millions of dollars in repair costs and losses in bandwidth capabilities. So our goal is to design a project that will be able to monitor cables, identify system threats, and hopefully prevent some of these damage incidents from occurring. So to start off, we're going to go over just a few major things here. First of all, here is a map of the current network that is in the oceans right now. You can see there's well over 300 individual cable systems working right now, and of those, 53 are transoceanic or the long-haul systems that go in between the continents. Nearly $12 billion has been invested in this cable system in the last 6 years, and there are 31 new systems coming online worth almost $5 billion in the next couple years. So what's driving this growth? There's a huge increase in the demand for international bandwidth over the last few years, as you can see on this chart. At the year end of 2013, there was 87 terabit per second capability of bandwidth across the entire world, and that is projected to grow into the 700 terabit per second range via planned projects that are currently in development. So what causes damage to the cable system? There's a few major causes, but the biggest one by far is accidental damage caused by fishing and shipping activities, as you can see on this chart here. Over 20% of the causes, though, are unknown, as you can also see on the far right side. Of all of these damage incidents, it's also important to note that approximately 70% of them occur in the littoral zone or coastal areas of shallow water. One of the major problems that we've run into with this project, and we think is causing some of the problems out there, is that there is no kind of mandated reporting or logging of these damage incidents. Even in this major study done by Telco Telecommunications, there are still a great number of faults that were not accounted for in this study. So one of the main issues facing our project is the lack of data, and we hope that increasing the amount of data we're going to get through this project is going to help significantly in preventing new damage incidents.
So in the case that a threat becomes a fault, this is the current repair process that occurs. The first part is finding the fault location and notifying the repair ship, which can be delayed due to inaccurate or slow fault location information. The second part is the ship travel. It can be delayed due to inaccurate fault location and poor weather. Finally, the last part is the actual repair, which can also be delayed due to inaccurate or slow fault location information. Therefore, our problem statement is that there are over 150 cable faults that happen every year, primary causes of which are fishing and anchoring incidents. 20% of them are unknown, which could be due to espionage and sabotage, and an average of 3 weeks and over $3 million of costs is due to repair damage. Thus, there's a need to increase surveillance of cables in order to decrease the number of faults, increase the rate of detection, and increase the availability of the cable system.
All right, so now we're going to go over our operational concept and the solution that we've come up with for this problem. For our system objectives, we've identified 3 major functions that need to be accomplished. First is threat identification. We want to identify both surface level threats like commercial shipping and fishing vessels, as well as underwater threats. Next is prevention and monitoring. We want to prevent faults before they happen by monitoring shipping and fishing. And lastly, repair coordination. So we want to notify repair companies of fault type and location for faster repair. Here's a table showing our design alternatives for the first function, which was threat identification. In the top left, we have the automatic identification system. This is a transponder that's required by law to be on all ships over 299 tons. It has about a 200 nautical mile range from the shore. It's actually currently being used, but more in a reactive system rather than a preventative system, which we're looking to use. The next 3 are autonomous underwater vehicles. They're basically underwater drones that can maneuver through the water in a predetermined path or by using sensors such as sonar. The sonar that these autonomous underwater vehicles will be using is a synthetic aperture sonar. It's a high-powered sonar system that can produce high-resolution images. Last alternative at the bottom is a hydrophone array. These are stationary nodes that are positioned along the length of the cable. So instead of actively going out and looking for threats, they are listening for noise created by the threats, whether it's an engine noise or a suspicious diver with its oxygen tanks. Here's a summary of the design terms that I just mentioned. On the left, you can see the AIS system on the shipping and fishing vessels. In the middle, we have the hydrophone array with the buoy at the top, which can transmit data to a source based on the sensors and the data that it receives. And on the right, we have the AUVs, or autonomous underwater vehicles, which have different types of capabilities.
So because there's so many moving parts to the system, we envision having a centralized location where we can process all the information, identify threats, and carry out prevention mechanisms. This centralized location is denoted by the bold black box that's around the three major functions. We call this mission control. The three major functions, identification, prevention, and coordination of repair, all take place within that black box. On the left side of this diagram, you see the threats that enter the system. This is the surface level activity and the underwater activity. These threats are picked up by our sonar sensors, which are the second box, and that information is sent into the identification mechanism of mission control. Once in mission control, we can then combine that with historical data to find out the probability of a threat occurring and a fault occurring, and take all that information and send it to the prevention block. The prevention block can then send messages out to the threats in order to create deterrence, or they can send messages out to the authorities in order to alert them that a fault is potentially going to take place. However, if this fails, that fault data is then combined with the cable performance data to identify the location of the fault and the type of fault, and then sent out to the repair coordination function, which will then contact repair companies in order to facilitate repair.
Next, we're looking at the simulation that we designed in order to research this problem. So a few major things we want to look at here is the effectiveness of single technologies, combinations of technologies, and full versus partial coverage of the protected cable. This can be important because we aren't sure how each of these technologies is going to work, and we may be able to find combinations of technology that work better than any single one. We also want to determine the utility and cost of these cables, cables protection systems, and hopefully verify our results. Here's our design of experiment for this. The first one we were going to test was on the cable called the SEA-US that goes through the Pacific Ocean. You can see the different types of systems that we are looking at testing and the different coverage percentages that each of those systems offers to the cable. Here is our simulation model, how we're actually going to simulate the TCPS system. In green, we have our simulation inputs and outputs. We're going to be bringing in our TCPS agent data and our cable profile for the cable that we're going to be looking at, and then outputting all the data that we're recording from that simulation. In red, we have our threat generation and threat default conversion. We are estimating that based on real-world data that we have found, and we have our three TCPS functions, identification, prevention, and repair coordination, modeled in their respective colored boxes. Go into a little bit first on our inputs. So here's a chart that shows the sample input for one of our hybrid protection cases. You can see all the different types of TCPS technologies that are going to be active on the cable and the ranges and speeds that they're able to move at. Here's a look at the cable profile that we inputted. We used the NOAA bathymetric maps in order to find depth profiles and input that into the simulation system as shown below. And here for our threat generation, this was kind of the one where we had to get a little creative. Because there simply is not data on the actual threats. There is only data on the actual faults that happen. So by using the fault data, we made some estimations in order to add in espionage and sabotage chances so that our simulation will be able to detect those. And then we normalized that data, estimated about a 50% chance of a fault on a single cable per year, and then created a threat default conversion probability based on the type of fault. For example, we think phishing is a fairly as important threat, so it's only got a 5% chance of a threat default conversion, whereas sabotage is a huge threat, so it's got a 100% threat default conversion chance. From that, we were able to calculate the estimated inter-arrival time of all threats, which is about 1,390 hours in between serious threats on the cable system. And we simulated that with a Poisson distribution in the Java simulation. For our threat generation, we also created a loiter time, which is the amount of time that the threat would stay in the cable system. This is the amount of time that the TCPS system has to detect and prevent the threat. We base this based on estimates on the different types of threats. And for our outputs, so first the simulation is a Monte Carlo simulation. We ran 7,700 replications per run, and the clock in the simulation runs for 10 hours, and it ticks on an hourly basis, so 87,000 ticks. And the idea is all of this data that it's tracking is being output for each of these lines, so we could get good statistical data from that. Looking at our first results here, we've got the SEA US simulation output. For the as-is case, obviously nothing was detected, nothing was prevented, and then you can see the data for each of our different alternatives here. The major ones to point out are the hydrophone and the second hybrid case of 4 AISs and the 1,000 hydrophone buoys. Both detected a huge amount of the different threats on the cable system and were able to prevent a significant amount. Also of note, at the very bottom is the hybrid partial coverage case, which was able to detect a significant amount and prevent quite a few as well, while at a very lower cost compared to the other options. A little more on that, we can look at the costs that were generated by the simulation output. So for the as-is system over 10 years, we're estimating about 1,300 hours of downtime and about $10 million in damages and losses over that 10-year period, with an availability of below 99% or only a single 9. Whereas for our hydrophone cases, we're able to improve those dramatically, cutting the downtime and the repair costs and bandwidth losses in approximately half, and increasing the availability of the cable system by almost a full percentage. You can also see at the bottom again the partial coverage hybrid. It was also very competitive, being able to significantly reduce losses while significantly increasing uptime, just not quite as much as the full coverage cases.
So in order to evaluate the outputs of the simulation, we constructed this utility hierarchy. The 4 major categories of the utility hierarchy are consistent with the requirements. So the first one is prevention, the second one is identification, third one is availability, and the fourth one is environmental impact. These are sample weights that are all we came up with based off our research. However, once the cable is actually in place, we can then utilize the data that we get from cable companies in order to make accurate weights. So the outputs of the simulation are then plotted on this graph with cost versus utility. As you can see in the top left, you get the highest utility cases. That's the hybrid case 2 and the hydrophone case. These provide about 0.7 utility, and the cost is about $12 to $13 million. However, if you go down to slightly about 0.5, 0.6 range, you see the 3 other hybrid cases. These are partial coverage cases. They provide pretty high utility, but the significant portion is that the cost is less than about $1 to $2 million. That's 12 to 13 times less than the other 2 cases. This means that depending on what the stakeholder wants, we can then provide a design alternative which best suits their recommendation for either coverage or cost. Finally, we evaluated the sensitivity to find out just how strong our results are. These are the most important weighting measures that had the most sensitive results. As you can see, they're not very sensitive. The one on the top left has a sensitivity about 0.4. However, the other 2 have basically no sensitivity. That means even if you change the weightings from 0 to 100, there's no difference in the top design alternative.
So for our recommendation, we've discovered that high levels of protection can be achieved with constant monitoring of high-risk areas such as littoral zones. A combination of AIS, hydrophone arrays, and even wave gliders provides a low-cost solution for the best protection. And lastly, a mission control center is necessary for prevention and repair coordination, where we will be able to send relevant messages to the appropriate authorities. Thank you for listening, and hope you enjoyed our presentation.